Good evening and welcome to our fourth Zoom session for Survey of Contemporary Mathematics. This week we are going to be focusing on chapters 7 and 8. A lot of chapter 7 involves some graphs. We're actually going to be looking at some problems from your textbook. I have some pictures printed out that we'll be referring to. But if you have your textbook available, you may want to open that up. You may more clearly see some of those problems from your own book as we go through those. Just want to review a few definitions with you from chapter 7. Graphs are displays that provide a pictorial representation of data. The advantage of graphs is that they present information in a way that is easily read. So some of the graphs we're going to look at this week are pictographs, circle graphs, bar graphs, broken line graphs, histograms, frequency tables, and box and whisker plots. Some other definitions you'll want to review for statistical measures are mean, median, mode, and range. Those definitions are: mean is the average. Okay, this is where we add the numbers up and divide them by how many there are. That'll give us the average of that group of numbers. The median is the middle number when those numbers are arranged in order. Sometimes there'll be just one number in the middle. If there are two numbers in the middle, you'll need to average those two numbers to find the middle of those, to find the exact middle of the whole set. The mode is the number that occurs most often. It is possible to have more than one mode. If all of the numbers occur just once, then there would be no mode. And range is the largest number minus the smallest number. And you actually need to subtract to find out what that range actually is. So we are going to be looking at some problems from page 335, 336 in your textbook. I'll try to zoom in and refocus for each problem if I can. But like I say, you might more clearly see this in your own textbook if you want to make that available to yourself. So in this first picture, we have a circle graph. This shows the approximate amounts of money that government agencies spent on maintaining internet websites for a 3-year period. One thing I want to encourage you to do as you look at the information presented to you, be sure and read all the information related to that graph, okay? What's hidden into this information is some very valuable information that might be missed if you're just looking at this circle graph. These amounts are in millions of dollars. Okay, so the Department of Defense is not just spending $148, but $148 million. So that's a very big difference in those amounts. So you'll want to make sure you label that properly. Okay, so let's answer some questions. It says, find the total amount of money that these agencies spent on maintaining websites. So total involves adding all of those sectors together. As you add those all together, you're going to get 349. But remember, that is in millions. So make sure to list the appropriate amount. So this is your hundreds section, thousands, and then this is millions. $349 million spent maintaining those websites. All right, the next question is, what is the ratio of the amount spent by the Department of Commerce to the amount spent by the EPA? One thing you're going to see this week is a lot of the topics that we have covered in those previous chapters are going to come back now, and we're actually going to use those in this new information. You're going to see words like ratio, okay? We're going to talk about percents and different things. So don't forget what we've already learned. Remember, ratios can be given as a fraction with a colon or with the word to. So I'll refresh your memory on what those look like. If a problem does not specifically ask for a type, then I'm open to whichever version you want to give. But make sure you read that problem carefully and give it in whatever form it asks for. So the ratio of the amount spent by the Department of Commerce to the amount spent by EPA. So that's how I'm going to set it up. It's very important that you set up a ratio in the order that it asks for. So the Department of Commerce spends $27 million, okay? I'm just going to write that out, $27 million to EPA spends $24 million. Now, I'm writing this out, but the 6 zeros that make up that million, notice that they're going to just completely cancel each other out. We will reduce ratios as far as we can, but we will keep ratios as improper fractions. We would never turn an improper fraction for a ratio into a mixed number. So I will reduce this. Both the top and bottom are divisible by 3. So that would be 9 to 8. Okay. So this is the correct answer, 9 to 8. You can write that as a fraction with a colon or with the word 2. Notice not only did millions cancel, but even the dollar signs, you know, those labels all reduced. So my answer is just this fraction form because those were all in the same unit of measure there. Okay, so make sure to reduce it down, but give it in the order asked for. If you had answered this 8 to 9, that would be incorrect because that's not the same. All right, number 3 asks for the percent of the total money spent. Okay, what percent? So my answer is going to be given as a percentage of the total money spent did NASA spend. So the question is, how much did NASA spend out of the total amount that was spent? We're going to round to the nearest 1/10 of a percent. Okay, so NASA spent $31 million out of a total of $349 million. So I'm going to start in fraction form. $31 million out of $349 million. So of course the zeros all cancel just like they did in this last problem. That is a fraction answer. So I need to now convert this to a percent. I'm going to go from a fraction to a decimal to a percent. And if you remember that from the last lesson, I'll take my numerator 31 and divide that by the denominator 349. That's my decimal. Once again, I'm going to say this again, do not round yet. I'm going to multiply by 100. It's going to shift that decimal 2 spots to the right, and I'm going to convert this to a percent. Okay. Now that it's in percent form, now I'm going to round to the nearest 1/10 of a percent. Okay, but not before. Convert it to a percent and then we round. The 10th place is right behind the decimal, but I look at the very next digit, 5 or more, bump up the score. So this will be approximately 8.9%, rounded to the nearest 10th place. All right, so the next graph we have is a double line graph. This shows the populations of California and Texas for selected years. Okay, so you can see California is the red line. Texas is the blue line. This axis shows the years. Notice the intervals. It's going every 25 years, okay? And then you can see the population is increasing, not 10 people, 20 people, 30 people, but once again, that's in millions, okay? So some questions are, in 1900, which state had the larger population? So I'm going to look over here on my graph. In 1900, if you look closely, the blue line is just above the red line. So in 1900, Texas had the larger population. In 2000, approximately how much greater was the population of California than the population of Texas? So I'm going to take a look over here at 2000, okay? So I can see right here, Texas would be about 20 million, okay? California is right above 30, but it's not quite halfway. We're just going to kind of get close here. That's going to look to be about, if you're looking in your textbook, this is actually has some extra marks on the side. It's not going to show up here on the screen, but you can see that in your book. It's really going to look like it's right there at 32. And once again, that's million. So what I want to do is see how much greater was the population of California. So we're going to find the difference. 32 million minus 20 million. That's going to be a difference of 12 million people. I don't mind if you label it 12 million. That's fine as well. Okay. Do your zeros. Make sure you have enough. During which 25-year period did the population of Texas increase the least? Okay. As you take a look at these graphs, to determine where the least change is, you're looking for the section that is the closest to being horizontal. And I think you're going to be able to see that right there, okay? The steeper line, okay, the more it has grown in that interval, okay? So this here, you know, would show that, you know, California's grown rapidly here, but by Texas being almost horizontal, this shows the how did it word that? The least increase in population. And it asks which 25-year period. You're not going to just answer that 1925 or 1950, but you're showing that interval of time from 1925 to 1950. That's the interval over which it has increased the least. Okay. Sometimes you might be asked to give an interval of time and you'll do it like that. And be sure to show each individual interval. Okay. Maybe if it asks which intervals did it grow the least, you wouldn't just say 1900 to 1950. You'd need to break it up 1900 to 1925, 1925 to 1950. So make sure you individualize those intervals on the questions this week. All right. Our next graph, this is another line graph here. This is a frequency polygon, shows the range of scores for the first 80 games of a season for the New York Knicks basketball team. Okay. So let's just try to interpret this graph. Notice there's a broken portion in this line, okay? The reason that is there is because never did they score less than 60 points in a game. So it was no reason to show all of those digits on this line, this graph. So that's why we sometimes see that broken line graph, okay? But you can see from 60 onward, it's increasing consistently 10 points, 10 points, 10 points each time. So these are the points scored, and these are the number of games in which they scored those points. Now I'm going to go ahead and just kind of take a look and see how high these points actually go up. Now I've done this ahead of time. You can look closely in your textbook to find these numbers. Okay, and let me just point out what I'm doing here. So like this point is right between 1 and 2. See, this is counting by twos. So I would mark that at 1. This point right here is between 6 and 8. So that's why I've marked it at 7. Okay, so I've already gotten these numbers ahead of time. All right, so now we're going to use this information to answer our questions. Find the number of games in which fewer than 100 points were scored by the Knicks. Okay, so here's where 100 points have been scored. All of these games right here, okay, from here on, they've scored less than 100 points. So we're going to add 31 plus 15 plus 7 plus 1. And that's going to total up to be 54 games. That's the number of games that they scored fewer than 100 points. All right, number 8 asks, again, what is the ratio of the number of games in which 90 to 100 points were scored to the number of games in which 110 to 120 points were scored? All right, so that's what I'm looking for. Those are the two things I'm comparing. I'm going to set it up as a ratio. So 90 to 100 would be this section right here. And if you look up, 31 games fall within that interval. Okay. To 110 to 120. So between this section right here, there's only 8 games that fall in that region. So the ratio is 31 to 8. Remember, leave it as an improper fraction. You would reduce it if you could. You can give it as a fraction, as a colon, or with the word to, unless it asks for a specific form. All right, another one. In what percent of the games were 110 points or more scored? We're going to round to the nearest tenth of a percent. All right, so 110 points or more. So I'm looking right here over. So from 110, it's going to be this 8 plus 1. Okay, so only 9 games did they score 110 points or more out of a total of, if I look back up here, it says this chart represents the first 80 games. If I were to go add up all these numbers, it should add up to be 80. So 90 games out of a total of 80. That's my fraction. Okay, so once again, I'm going to come over to my calculator. 9 divided by 80. There's my decimal. Do not round yet. Times 100 shifts that decimal 2 spaces to the right. So this is exactly 11.25%. Okay, but it asked me to round. So I'm going to do that. 2 is in the tenths place. Number right behind that, 5 or more, bump up the score. So that's going to be 11.3%. Okay. Sometimes it might ask you to round to the nearest whole percent. That means we don't want a decimal. If that was the case, this would round to just 11%. So you just read that question carefully. Make sure you know your decimal places. It goes tenths, hundredths, thousandths, and so on. You round to that position, and you don't need to see anything after that position. Any questions on that
No.
page?
No. No, ma'am.
Okay. All right, so this next one is an example of a pictograph. It's a graph that involves pictures. So this shows the number of passengers who boarded planes in the 5 U.S. airports in a recent year. All right, so let's take a look at, we've got different airports we're comparing. This is what we call the key. This is important to us because it shows us what does this picture represent. One suitcase represents 10 million passengers. I think that was going to say per year. So 10 million passengers. So half of a suitcase would represent half of that amount. Half of 10 is 5 million. So full suitcase is 10 million. Half a suitcase would represent 5 million passengers. So what that means is in O'Hare, there are 10, 20, 35. So that would be 35 million passengers. In Hartsfield would be 10, 20, 30, 40 million passengers, and so on. So that's how you use that information. All right, so number 10 says, how many more passengers boarded planes in O'Hare each year than boarded planes in the Denver airport each year? So I'm about to compare O'Hare to Denver. So I've already added that up. Denver is 10, 20, 5 million. So how many more boarded planes here than here? If I subtract those to find the difference, okay, 35 minus 25, that would be 10 million passengers. And you can use the word, or you can use, the appropriate amount of zeros. All right, 11, here we go again, another ratio. What is the ratio of the number of passengers boarding planes in the Hartsfield Airport to the number of passengers boarding planes in the Dallas-Fort Worth airport each year. Here, write your answer using a colon. Okay, so that's what I need this time. So I always start with a fraction. That's just me. Hartsfield, he said that was 40 million. Okay, to the Dallas-Fort Worth, 10, 20, 30. Okay, I want to reduce it. Both of these numbers are divisible by 10. So that's the same as 4 to 3. But I'm going to give that final answer as a colon. That's what it asks for, 4 to 3. There definitely is one about a pictograph on the apply this week, so make sure you can interpret it based off of this example. Okay. All right. Next photo is a double bar graph. Okay, this is a bar graph, but notice it's got 2 bars side by side, so we're not only comparing, you know, the different regions here, but also 2 pieces of information for even just that one region. So this shows the total number of days open and the number of days of full operation for ski resorts in different regions of the country. So I've got different regions here, and then this axis is how many days, okay? Notice they're counting 10, 20, 30, 40, 50, and so on. Purple is days of full operation, where blue is the number of days that they're open. Now, once again, before I start, you know, reading into all these questions, I want to see how high do these bars go up. So this one would be right at 60, 10, 20, 30. So that's going to be 130. That's how you're going to, you know, investigate what that goes to. You're just going to have to count and find that. Now, I've also looked at these ahead of time. So just to save our time, I'm just going to fill those in. But you'll want to carefully interpret that, because if you get these numbers off, then of course that's going to mess up your information over here. All right, so number 12 says find the difference between the total number of days open and the number of days of full operation for Midwest ski area. So here's Midwest right here. It's open 90 days, but it's in full operation only 40 days. So what is the difference between those bars? 90 minus 40, that would be 50 days. All right, for the Rocky Mountain ski areas, what percent of the total number of days open was the number of days of full operation? Okay, so this time I'm looking for a percent. All right, so Rocky Mountain, here we go. All right, so it is in full operation 70 of the 140 days, okay? So 70 out of 140 days. I can reduce that, divide it by 10. 7 over 14 is also 1/2. 1 divided by 2, you know that, it's 0.5. Okay. Times it by 100, shift that over, that's going to be 50%. Okay. Which region had the lowest number of days of full operation? Okay, lowest number of days in full operation, that's the lowest purple bar. That would be Southeast. Okay. But then we have another question. How many days of full operation did that region have? And so I'm now going to answer that with 30 days. So there may be some questions this week that have 2 parts. Make sure you answer those completely. All right, I'm going to jump on down and do one final graph for chapter 7 before we move on. This is a histogram. It's based on a Gallup poll survey. This figure shows the numbers of hours that 46 people slept during a typical weekday night. Okay, so here we've got the hours sleep per night, under 6 hours, It was 5 people. 6 hours. Let's see, that counts up 1, 2, 3, 4, 5. So 10, 11, 12, 13. I'm just going to go ahead and fill those in. And we'll see how many people actually slept those number of hours. Now remember over here it just said 46 people. So if I add these numbers together, that should total up to be the 46 people that were surveyed. So 16, how many people surveyed slept 8 hours or more? So 8 hours or more would include 12 plus 2 plus 1. And so that would be 15 people in all. And then final question here, what percent of the people surveyed slept 7 hours? Round to the nearest 10th of a percent. So how many slept 7 hours? Right here, 7 hours goes up to 13. 13 people slept 7 hours out of a total of 46. Okay, so there's my fraction. So now I'm going to come over here, 13 divided by 46. There's my decimal. We're rounding to the nearest 10th, but before I do that, multiply it by 100, shift that decimal over 2 spaces to the right. Here's the 10th place. The number behind that is 5 or more. Bump up the score. That's going to be 28.3%. 4 or less, let it rest. 5 or more, bump up. Into those little details. All right. So that's chapter 7. I do want to say that most people do very well on chapter 7. You might come away thinking it's too easy. I hope you do. Don't overthink some of those problems because they may just actually be that easy. So, you know, really read those, pay attention to the details about how you're to give your answers, where to round. But if you come out thinking that was easier than you thought, it just may have been. And so take it and run with it, but just make sure you pay attention to those details. All right, we're going to run into chapter 8 now. Chapter 8 is all about converting from one unit of measure to another. We're using conversion rates, multipliers. I will refer to this chart some. This is just going to help us do some converting with liquids. The G per gallon. Okay, in 1 gallon there are 4 quarts. In each quart there are 2 pints.
2 quarts.
In 1 pint there are 2 cups. So some of this, you know, you're going to know. Honestly, you may not have memorized all of this, but you can Google any of this information. Here are some other equivalent units that we'll be converting with. A lot of this you'll know, 12 inches in a foot, 3 feet in a yard, 16 ounces in a pound, that kind of thing. Okay, I'll refer back to this as we work through here. But of course, all of that information is available online if you've forgotten those conversions. I'm going to do this the way the textbook does, using conversion rates. You may totally understand this your own mental way. That is fine, okay? So I'm not asking you to show me work or do anything different than you would. I'm just going to stick to the method that the textbook uses. That is conversion rates. So here I'm going to convert 64 inches into feet. So what I need to do is understand what is the relationship between inches and feet. Well, my chart says that 12 inches is equivalent to 1 feet.
Yeah.
Okay, so I know that. Here's what that means for me. That means that I can set up what we call 2 different unit multipliers. 12 inches over 1 foot or 1 foot over 12 inches. Now these don't look like one whole, but they are, okay? Because these are equivalent units of measure, putting one on top of the other is the same as if I had 5 over 5 or 3/3 or 7/7. Those are equal to 1. A number divided by itself is always equal to 1. Now, I know those don't look the same, and I'm not saying that 12 and 1 are the same number, but I'm saying 12 inches is the same as 1 foot. 1 foot is the same as 12 inches. And because those units of measure are the same, we can put them in this fraction form because they just represent 1. And I can multiply anything times 1, and I get that same value back. It just is going to be converted into a different unit of measure. And so that's this method that your textbook shows, is using the conversion rates to go from one unit to the other. So you have to consider, what do I have? I have inches, and I want to convert that to feet. So I will pick whichever one of these units of measure that will cancel inches and leave feet. Since I have inches, I'm going to use the second one here, 1 foot over 12 inches, because I can reduce these units of measure diagonally, and feet is what's left over. So 64 times 1 divided by 12. Okay? 64 times 1 divided by 12. Notice I'm going to get this answer when I do that. I do not want you to round with decimals unless it says you can, okay? So obviously this is not dividing evenly, but with these units, these measures I'm converting, I'm probably going to be getting a lot of mixed numbers on this assignment. So I'm going to actually divide 64 by 12. Even though this doesn't divide evenly, I do know where to start. It says it goes in 5 times. 5 times 12 is 60 with 4 left over. So see, this is my answer, 5 and 4/12, okay? 5 and 4/12, which is the same as 5 and 1/3 feet. So 64 inches, dividing it by 12, I get 5 and 1/3 feet. These are equivalent in lengths. They're just 2 different units of measure. In this next one, I'm still using feet and inches, but this time I have feet and I want to change that into inches. I'm converting that into inches. Okay? So because I have feet, I'll use this unit of measure this time. 12 inches over 1 foot. Okay? The feet cancel diagonally. Inches is the only unit of measure left over. Notice I'm not dividing, but I'm multiplying this time. 9 times 12 would be 108 inches. Now, it's going to be very important that you label this week, because if you put 108 feet, you're going to get points deducted because that's not the same as 9 feet. So pay attention to the fact that we're converting units of measure. So not only will the number be important, but that label will be as well. We can do all kinds of different operations. We can add, subtract, multiply, divide, any of that kind of stuff. We're adding mixed measures here, so when you do that, you'll want to line up those like measures and only add the same units together. 7 plus 4 is 11 inches. 6 plus 3 is 9 feet. If this had been 12 inches, then I would simplify that to 10 feet. Okay, so we might be asked to do some simplifying in that way. One thing I want you to be careful about is, notice I didn't drop the 1 and carry that other one. This is not like adding normal numbers where you carry over. Okay, so we're just kind of keeping those units separate. This one, I'm going to work this one. It's really similar to what I have up here. I have inches, okay? But this time, I don't just want a feet answer. I want inches as well. This is going to be taking an answer in inches and giving an answer as mixed unit of measure. I know that, like I did up here, to go from inches to feet, I had to divide by 12. So I'm going to take 100 and divide by 12. This is not going to divide evenly here. Okay. It doesn't divide evenly. And I'm definitely not going to write 8 feet 3 inches. That is not a thing. Okay. That's not how those decimals work. But this 8 tells me at least how to start. 8 times 12 is 96. And I can subtract and get 4 left over. So 100 is exactly 8 feet and 4 inches. If I was trying to do what I did up here and just get a foot answer, it would be 8 4/12 or 8 1/3 feet. But as a mixed measure, it's 8 feet, and the leftovers here, that's my inches that were remaining, okay? So just be careful. You might, depending on the question, you might have to go all the way to convert to a different unit of measure or give it as a mixed unit of measure. Here we have the average height of a player in the NBA is 6 feet, 6.98 inches. Find the average height in inches of a player in the NBA. So notice I have feet and inches, but my answer just wants the full amount in inches. Okay, so I'm going to have to do some converting. I have feet. I need to change that to inches. What did I do back here? I multiplied times 12. So you're really going to have to pay attention. Do I divide? Do I multiply? When do I do what? Okay, those unit of measures will help you to know how to set those up. So in this case, I've got 6 feet. I've got 12 inches over 1 foot. Those cancel. 6 times 12 is going to be 72. But don't forget that little part right there. I'm going to have to add that to it to get the total amount of the average height of an NBA basketball player in inches. Okay, so watch that label. I converted it all to inches. Next one, a board that's 6 2/3 foot long. It's cut into 4 equal pieces. How long is each piece? So let me write this out. I have a board that's 6 2/3 foot. I am dividing that into 4 equal parts. This goes way back to week 1. I am dividing with fractions. When I'm dividing with mixed numbers, even multiplying with mixed numbers, I must first turn this into an improper fraction. 3 times 6 is 18 plus 2, that is 20. We keep the same denominator. Divided by 4. I'm going to write that as 4/1. When we divide with fractions, we're going to leave, change, flip. Okay? Leave,
change, flip.
We multiply the top numbers together, that would be 20. Multiply the bottom numbers together, that would be 12. Okay?
Change, flip.
Now, we're talking about like, we got a construction project going on. I need to know how long, I'm going to measure those 4 pieces out. I'm not going to leave my answer this way, okay? 20 divided by 12 does not divide evenly, okay? So I'm going to come over here and do that math. It's going to go in 1 time with 8 left over. So each board is going to be 1 8/12. I'm going to reduce that. Both are divisible by 4. So that's going to be 1 2/3. What's my label here? I'm still in feet. 1 2/3 feet. I'm going to just keep pressing on because I'm just trying to give a variety of examples so you just have enough practice problems to look back to as you prepare for your apply. We can go back over any of these if you have some questions in a little bit. If you're watching this later, our code word tonight is average. You can email me brief summary with that code word to get your extra credit points. Let's take a look at this one. This is another mixed measure. I'm going to subtract.
Don't get that.
All right, now here's something we got to be careful about. Just like before, when I'm adding, I don't do this like normal addition. I also
Right.
don't subtract it like normal subtraction. I cannot take 8 from 5, and it's not like I borrow here and make that a 15, okay? I will have to borrow, but it's going to involve regrouping because I'm going from one unit of measure to another. Now, on my chart, it says, let me write this out, that 1 pound is 16 ounces. So I am going to borrow a pound, but when I add that back, I'm adding it back as 16 ounces to the 5 I already have, and that makes 21 ounces. If I borrow a pound, that's 16 ounces that I'll add to that 5 I had. That makes 21. Now I can subtract 8 from 21.
Oh my God.
21 minus 8 will be 13 ounces. 6 minus 3 is 3 pounds. So that's my final answer there. Let me say one thing about labeling. I do not mind if you abbreviate. That doesn't bother me at all. But make sure you can read your own handwriting. Don't accidentally tell me this answer is 31 pounds and 130 ounces. You know, make sure you separate your numbers from your labels and don't misinterpret the answer that you mean to give me, okay? Because I can only grade what you submit, not what I think maybe you meant. So be careful with that. Here's a multiplication with mixed numbers, 5 1/2 times 6. Once again, when we have mixed numbers, I need to turn this into an improper fraction. 5 times 2 is 10, plus 1, that's 11 halves, times 6 over 1.
66.
And that will divide evenly. That's going to be 33. My label, 33 pounds.
Mm-hmm.
Right here, I'm taking this mixed measure and I'm dividing it by 2. So I'm going to have to divide into each one here. 3 divided by 2 is 1. And I have 1 pound left over, okay? 1 pound, we said a minute ago, was 16 ounces. I'm going to change that over. 1 pound now, so that I can combine it with this section right here. That would make 24 ounces. And then I can divide 24 by 2, and that will be 12. And that'll divide evenly. So that answer would be 1 pound, 12 ounces. Maybe you think of a different way to work that out. I mean, if it doesn't specifically ask for a certain unit of measure, you know, maybe you want to convert everything to ounces and then divide it by 2. I don't know if that would be better for you to interpret that way, but there's an example if you have one like that this week. Okay. All right, I want to do a few more problems before we close. Some of the things, I'm going to give that example. Some of the problems we do this week are going to involve multiple steps. So I just want to encourage you to be careful as you go through those multiple steps. This is one of those things right here. The manuscript weighs 2 pounds, 3 ounces. It's mailed at the rate of 44 cents per ounce. So we're going to find the cost to mail that manuscript. This package is given to me in a mixed measure, pound and ounces, but I'm charged per ounce. So I've got to take this and convert it to ounce before I can find out how much it's going to cost. So 1 pounds is 16 ounces. 2 pounds times 2 would be 32 ounces. 2 pounds would be 16 plus 16, so 32 ounces. Combine that with that 3, and that's a total of 35 ounces, okay? So that's how much this package weighs, and it's going to cost me 44 cents per ounce. So I'm going to need to multiply that together to find the total cost for this manuscript, and that number is going to be $15.40. So we had to convert it to a different unit of measure and then use that answer to find out the cost. All right, here's a good one. A college bookstore received 1,200 textbooks, each weighing 9 ounces. Find the total weight of the 1,200 textbooks in pounds. So you got to read this carefully. Read it 2 or 3 times, you know, if you have to understand what's given to you, what's it asking. I know the weight in ounces, but I'm looking for the weight in pounds, okay? So let's work with what we got so far. 1,200 books, each weigh 9 ounces. So let's multiply that to see what is the total number of ounces of those books. If I multiply that, I get 10,800 ounces. All those books weigh that much. Okay. Now I want to convert from ounces to pounds. Okay. So 1 pound is 16 ounces. This goes on the bottom so that it can cancel diagonally with that unit of measure. Pounds is the only thing left over. 10,800 times 1 divided by 16. Okay. 10,800 divided by 16, that actually is going to divide evenly at 675 pounds. Okay. So we had to do one step, use that information, convert it to get another answer. I've got 2 final questions we're going to do tonight. Cafeteria sold 124 cartons of milk in a day. Each carton contained 1 cup of milk. So how many quarts of milk were sold that day? So 1 carton is 1 cup. If I have 124 cartons, then I have 124 cups of milk. I need to convert cups to quarts, okay? Convert cups to quarts. And if I look, I'll bring this back up here. 1 Q has 4 C's, okay? So that says 1 quart equals 4 cups. That's my conversion rate. 1 quart is equal to 4 cups. Cups can cancel diagonally. 124 times 1 divided by 4. That's going to be 31 quarts. The spa owner bought hand lotion in a 5-quart container and then repackaged the lotion in 8 fluid ounce bottles. The lotion in empty bottles cost $81.50, and each 8 fluid ounce bottle sold for $8.25. So how much profit was made on the 5-quart package of lotion? Okay. Lots of numbers here, lots of words. So let's go back and see if we can understand what's going on. So we bought it in a 5-quart container, repackaged and sold it in 8 fluid ounce bottles. So I've got to convert quarts to ounces. Okay. My paper says that there are 32 ounces in 1 quart. So I have 5 quarts. 5 times 32, okay, would be 160 ounces total. 1 quart is 32. 5 quarts would be 32 times 5, 160 ounces. We're taking all of that lotion and dividing it into 8-ounce bottles. So 160 divided by 8 tells me that we can get 20 bottles from that large container. Okay? Each bottle sells for $8.25. That's what it sells for. So I've got 20 bottles, multiply that times $8.25. So that's $165. Okay. But we all know that's not my profit because we have to subtract the expenses that are on the front end. Okay. The lotion and the empty bottles cost me something first, $81.50. And so if I subtract that, okay, whatever's left over is going to be my profit in the answer to this question. That will be $83.50. I'm pretty certain you're going to see a question like that this week. Like we did 1, 2, 3, 4, like 4 steps to this one problem. So you've got to really understand what's given to you. How do I carefully move from one part of that problem to the next to get to that final answer? 5 quarts is the same as 160 ounces. Divide that into 8 fluid ounce bottles, gives me 20 bottles. Sell for $8.25 each. I make $165 minus the expenses, gives me my profit. So follow this example to help you through that question. I'm sure you may have some questions this week. Please reach out. Reach out with problems so that I can help you as much as you need through the week. I'm going to pause the video now.